Well, greetings, Mr. Kolazar's class. We're going to start into video 7 looking at equilibrium expressions. Now, equilibrium expression is going to be a constant expression that can be used to calculate concentrations and take out solubilities. And we're going to add in to predict if the reactants or products are favored. Now, as we look at this, equilibrium constant is going to be this KEQ value. And KEQ is going to be our equilibrium constant, or kinetic equilibrium. Now, what it's going to look at is it's a ratio of products concentrations to reactant concentrations at equilibrium at a given temperature numerical value. It's only for aqueuses and gases, not solids and liquids. In our equation, what it's going to look like is if we had a reaction, and what we're looking at is W, X, Y, and Z would be from a balanced chemical equation, our BCE, and those are going to be the coefficients. And then our letters, the A, B, C, and D, or how many ever letters they might be, are going to represent our concentration, in moles of either the element or compound. And those are going to be shown in brackets. So brackets are going to show concentration. So as we're going, that's what we're looking at there. Now, what we're going to see is it's going to be the products to reactants. So our equation is written here, and our equation is going to show the products on top, and it's going to be the concentration of your product raised to the power of whatever the moles in front of the BCE are. So from the coefficient of the BCE, are on the top, divided by the concentration of the reactants raised to the power of whatever the coefficient is in front. So we're going to look through that. Now, when you get an answer, whatever the KEQ is, that answer, if it's greater than 1, it favors products at equilibrium. If it's less than 1, it favors the reactants at equilibrium. So to try this out, we have an equation here. Nitrogen plus hydrogen gas produces ammonia. And we notice that there's no 1 here, but there should be the number 1. We don't write the 1s, to a 3:2 ratio for each of these in this gases. So if we were to write out an equilibrium expression, we would write out the KEQ would equal the product's concentration, in this case NH3, to the second power. Now, since there's only one product, we leave the other one out, so there's nothing else, so you don't worry about writing anything else up top, divided by, in this case, we've got nitrogen, concentration to the first power, times the concentration of hydrogen to the third power. Now, if we're given this information, add this, so we can plug this in. So using this equation up above, KEQ, if we're given at equilibrium 0.77 moles of nitrogen, 0.2 moles of hydrogen, and 0.52 moles of ammonia, to plug those in, we would have up top our concentration of ammonia would be 0.52 to the second power. Remember, again, that comes from the balanced chemical equation. Part 2, our reactants, we would have from nitrogen 0.77 moles, and with nitrogen it's just to the first power, times the concentration of hydrogen 0.022 to the third power. Numbers on top, 0.52 squared divided by 0.77 times 0.22 cubed, so 0.22 times 0.22 times 0.22 would be cubed. In the end, our KEQ for this reaction is about 32.98 32.98, since it's greater than 1, favors our products. So our KEQ can show our established equilibrium favors the production of the products. Go ahead and just take that one out. And that will be it for establishing our KEQ, or equilibrium constant.